Okay, so this is week 6. We're going to continue example from tutorial on week 5 on thin wall, just to finish things off. Okay, I think the most difficult part is over. Then we're going to look at the last section of shearing stress, which is unsymmetrical loading. Okay, load on shearing stress. Then I'd like to make an announcement that quiz number 5 will be held on June 11 on the Friday, because I've been made aware that some of you will have term tests in June 10. Okay, so the time is the same, from 7 to 4 p.m. Okay, and then there'll be John, what time is the term test?
I think 7:30.
Okay,
Yeah,
so
I think it's 7 or 7:30. It's during lecture time.
okay, so if that's the case, I also will say that June 10, no tutorial. Okay. Yeah, so there'll be no tutorial on June 10, so there's no point having a tutorial when you guys are having a term test. Okay, so on that note, so this is the question we try to solve on our tutorial last Thursday. I did not really finish it. So the unique thing about this problem, just to very quickly recap, is when we construct the shear flow. Okay, when we construct the shear flow, which I'm doing now, right? So this is how the shear flow goes, right? So one will go to the left, one will go to the right. Right, so this is how the shear flow goes, right? And then when we analyze, we have to analyze relative to the centroid, right? So we have to analyze relative to the centroid. So this is our centroid. So the easy stuff, or what is familiar. So you know, down here we have a terminal, and at the end over here there are also terminals over here. So what is unique about this? Okay, if you look at the top, right, we know down here there's a gap, they're not really connected, right? So at the top, we know is very easy to do. Okay, the shear flow only goes one direction if we want to find the stresses at point D. But at the bottom, right, at the bottom, just to quickly recap, is we have flow coming down in one direction, right, and then going towards the left, and then it goes up again, right? So we form another rule, which the analysis cannot have reverse flow. Okay, so if we look at the lecture, sorry, if you look at the we have another rule. Okay, rule number 6: do not consider the Q in reverse. Okay, and I prove that to you is by calculating the shear flow at point D. Sorry, we did not calculate the shear stress. So how do we prove it? Okay, so how do we prove that the reverse flow cannot be considered? So when we look at point D, right, we consider this section, right? We consider this section from the top, right? And then we got a particular value, a unique value. Okay, so we got 21 with point D. Yeah, we got the A 21.981. Okay, and then we did the bottom. Okay, we did the bottom section. So if we take the bottom section, okay, if we were to take the bottom section, right, So if we were to take the bottom section, so bottom section is which section do we take? So I just proved to you that we cannot consider this entire section over here, right? You cannot consider the entire section down here because there's a reverse flow. When I say reverse flow, because this is coming down and this is going reverse, so you cannot do the reverse. And fundamentally, what is going on, and when we derive the rules, right, where you have V, Q is in one direction only. Okay, so mathematically, there is that restriction. Okay, so that's why it will not work if we take the reverse flow. And I can't remember whether did we consider the reverse flow. Yeah, we did consider the reverse flow, right? We consider twice the web, and then we get this first moment of area, which is wrong, right? So this is not a valid first moment of area, okay, when we consider the reverse flow, right? So what can be done, right, or what has to be done is, now what if we just consider, okay, what if we just consider this section in blue that we highlight in blue over here, right? What if we just consider, so there is no reverse flow into consideration for this case, right? There's no reverse flow. So we are going to work out that value. Oh, I think we did work out that value. Sorry, we did. Sorry, this is the value. Sorry, this is the value. Okay. So the first one in green, just to recap, I know this is a bit confusing for now, right? So when we did this one, okay, when we consider this is also consider the reverse flow, right? The first moment of area was 1752 millimeter cube, and that is not right because we cannot relate to 2352. So 2352 is from here. This is from the top, right? So if we just consider the blue section, right over here, right? So ignore the reverse flow, right? That's why this is just one web, right, and one lower flange. Okay, the one before is two web and one lower flange. So when we do that, we got our Q first moment of point D at 1176. Okay, so to calculate our shear stress at point D, right? So this will be equal to 5 times 10 to the power 3 multiplied by 1176 times 10 to the power minus 9. Okay, so this is 1176 times 10 to the power minus 9 meter cube, and then divide by the first moment of area, 133.75 times 10 to the power minus 9. And the thickness, there's only one thickness because there's only one Q, right? There's only one Q coming down here. Okay, there's only one Q. Not like over here, one Q go towards the left, one Q go towards the right. There's only one Q. So when we work this out, this will be equal to 5 power 3 times by 1176 power minus 9 divided by 133.75 power minus 9 divided by 0.02. So it will get 21.981. Okay, so this is by consider the bottom and ignore the reverse flow. Okay, well, this one, the one that's on top over here, This one we is looking at the top, and the answer has to be the same. Okay, so that is the most important thing. Okay, is the reverse flow. Now this you'll find useful also when later on where we are doing unsymmetrical shear. Okay, so I want you to get used to it. Okay, now let me continue with this problem. So I'm going to take here. So the next one we are going to consider, right? We are going to consider the shear stress at point C. Okay, we're going. So you can see where point C is in the diagram itself. Okay, so from here, I'm going to draw the centroid. Okay, so again, this is our centroid. And this is our Vy. And I'm going to draw, we have seen this before. I'm still going to draw the shear flow or the shear force axis. Okay, shear force axis. All right, so directly of the center. So this is our shear force. Right, now when we want to find the stress, the shear flow or the shear stress for point C, I want you to look at point E, what happened, right? So point E, right, at point E, we take this area because the Q is moving outwards or is flowing in that direction, right? At point C, right, we look at point C down here. Now the Q is coming back in this way, right? Towards the shear force axis. So by applying rule number, I think it's rule number 2 and 3, right? Where the analysis starts from the maximum. So the area to consider is here, right? So the analysis starts from Y max, right? Y max, right? And this is our analysis direction. Right, so Y max is the start, right? So it draw itself back. Okay, mathematically we derive it that way. Okay, that's why that is the rule that we came up with. So from here we want to find, so we can also see that it is a white flange. Okay, there's only a single Q, right? Because the left from the shear force axis and the right, they are not actually connected once below the centroid. Okay, so the Q at point C, so the width will be 12, the thickness will be 2, and the height or the Y bar will be 25, right? So this 12 times 2 times 25 is equal to 600 millimeter cube, or 600 times 10 to the power minus 9 meter cube. Okay, so the shear stress at point C is equal to VQ over IT, right? So the V is 5 times 10 to the power 3, multiplied by 600 times 10 to the power minus 9. The I is 133.75 times 10 to the power minus 9, and we just have 0.002. Okay. So this will be equal to 5 power 3 times 600 power minus 9.